Hi folks, we're going to take a look at number 4 from page 145. So this is a pretty typical optimization problem. So we've got a rectangular piece of cardboard that we're going to use to make an open top rectangular box, and we do that by cutting out squares from the corners. And they want to find the dimensions that gives the box with the largest volume. So this is kind of a representation here of what we have. So you notice I've cut off equally sized squares, and what we're going to do is we're just going to fold up the sides. Okay, and once we do that, well, we're going to have an open top box. Okay, so if you take a look at this here, you realize that I'm going to need the length, width, and height, and you realize that the length is just going to be the total length of the cardboard minus the two little pieces that we take off. Okay, the width is just going to be the total width minus the same two pieces, and you realize that the height of the box is just going to be the width of that piece that we've cut off. All right, so I'm going to draw a representation here, but just wanted to have you see what it looked like in 3D. Okay, so we've got, and we're going to cut off our corners. And what we don't know is how much to cut off. Okay, that's essentially what we're not told. So since we don't know how much we're cutting off, that's what I'm going to make my unknown. So I'll just call that X. And so what you realize is that this rectangle here represents the base of the box, and then you're going to be folding up all these sides. Remember that you're getting rid of these corners here. So again, if the total length is equal to 100, this part here is just going to be 100 minus 2x. We're just going to subtract the two parts of those corners that we've cut off. And if this total length is 40, it means that the width of the box is going to be 40 minus 2x. And then the height is just going to be x. All right. So I just write that out here. We've got length is going to be 100 minus 2x. Our width is going to be 40 minus 2x, and our height is going to be equal to just x. So if I'm trying to maximize the volume, which of course is just length times width times height, can now be rewritten as length, which is 100 minus 2x times 40 minus 2x times x. All right. So there's our model in terms of one variable. The only other thing we need to determine is what our domain is. So clearly x has to be greater than 0. Okay, so right off the bat we see we're not working with a closed interval. And in terms of the maximum value, well, this is where I'm going to focus in on the shorter side, because here remember that this width of the base is 40 minus 2x. So I can't have x being equal to or more than half of this side. So if it's equal to 20, I'd just be folding it in half. Not very useful, and certainly anything bigger than that wouldn't make sense, because I'd end up with a negative number here. You know, if I chose x to be 21, 40 minus 2 times 21 gives me a negative number. So it has to be strictly less than 20. Okay, so notice here I had to work with the shorter side. Wouldn't have made sense to work with the longer side. Okay, so there we go. We have our model, we have our domain. Now we can go ahead and do some calculus, but I think it makes more sense that I definitely don't want to apply the product rule a bunch of times here. So it makes much more sense to multiply this out. Okay, it's not too bad. So I'll start by multiplying out the binomials. So here we have, that'll be 4,000. This is negative 200, and this is going to be minus 80, so minus 280x, and then plus 4x squared times x, and then of course we've got, we'll clean this up here, so we'll say 4x cubed. This is going to be minus 280x squared, and then plus 4,000x. All right, so now we'll go to take the derivative on this here. It'll be much nicer. So we've got 12x squared. 2 times 280 is going to be 560 minus 560x, and then plus 4,000. Okay, and of course we want to determine when this is equal to 0, because we're going to start by looking for our critical numbers. Okay, now if I wasn't looking to if I wasn't looking to get approximations, which I do want here because it's an application question, I might try simplifying this, but since my calculator does all the work for me, I'm just going to put this straight in the quadratic formula without factoring out common factors. You certainly could do that, but like I said, since I'm going to be looking for approximations anywhere, I'm not going to worry anyway. I'm just going to go straight to the quadratic formula. So negative b, so that's going to be 560 plus or minus square root of 560 squared minus 4 times a, which is 12, times c, which is 4,000, okay, all over 2 times 12 is 24. All right, so let's get our trusty calculator out and calculate that. So I'm just going to calculate. I want to see if this square root is going to be bigger than or smaller than 560, because if it's going to be bigger than 560, then I know I don't have to deal with the subtraction. If it's less, then I might have two possible answers. All right, so I'm going to do the square root first. So 560 squared minus 4 times 12 times 4,000. Okay, and exponent 0.5 for the square root, and I see that it's less than. So I'm going to have to consider both here. So 560 plus or minus 348.7 over 24. All right, so let's calculate those here. So let's do plus 560 and then divided by 24, and we see 37.8. or 37.9, but doesn't really matter because I notice that that's not in my domain. So I'm not even going to be considering that possibility there. All right. So let's check the other one. So the other one, 560 minus 348.7 divided by 24, and that gives me 8.8, and that is in my domain. Okay, so I have to hope that that leads us to an absolute maximum on this interval. All right, so let's check v prime. Okay, now normally I would just be drawing from 0 to 20, but what I notice is that my derivative is a quadratic, and I want to determine when that's equal to 0. So I'm going to use, my knowledge of sketching polynomial functions. So here I've got 8.8. and I've got 37.9, okay, and I know that my parabola opens upward because it's a positive leading coefficient, okay, but of course I'm just interested from 0 to 20, and I see that at 8.8 I'm going from positive to negative, which means I have a local maximum at 8.8, but from 0 to 8.8 the function is constantly increasing, and then from 8.8 to 20 it's always decreasing. So this is indeed not just a local maximum, but on 0, 20 it's an absolute maximum. All right, so we found what we wanted in terms of the x value. Let's go back to our question and see what they're asking for, and they're looking for the dimensions. So I'm just going to take this x value and put it into here. So my answer is going to be that my height, well, that one's easy. We already have it. That's just 8.8 centimeters. Okay, so not a very tall box. Okay, our length is going to be 100 minus 2 times 8.8. is 82.4 centimeters, and then my width is going to be 40 minus 2 times 8.8, and that's going to be 22.4. All right, so there we have it. So once this unfreezes, there we go. We can just do a quick recap. So step number 1, get my diagram here, and since I'm looking to maximize volume of a rectangular prism, there's my starting expression, but of course this has 3 variables in it. I need to write it in terms of 1 variable, and that variable would be the length of the square that I was cutting off. So from this I was able to get expressions for length, width, and height, and then from there get my model with my domain based on the restrictions of the size of the cardboard, and then from there just apply my calculus. All right, that's it for this one.